All right, so this is going to be kind of a continuation of how to figure out where a polynomial is 0, positive, and negative. But now we're going to look at ratios of polynomials, and we're going to determine where a rational function is 0, positive, and negative, or even undefined. And that's the big difference between a rational, one of the big differences between a rational function and a polynomial function. So I will assume that you've already watched and already know how to use end behaviors, zeros, and multiplicities to make a number line chart for polynomials, because that's exactly what we're going to do here for rational functions. So the instructions for these examples will be create the number line sign chart. You could just call it a sign chart. You could just call it a number line chart. It's all the same. Now, the key to this is knowing end behaviors of your rational function. So again, I'm going to assume you know that, but of course, we will see it pop up many times throughout these examples. So it'll be a good refresher. So the first function we'll look at is y equals x minus 4 over x plus 3. Now, we can call them zeros for this function, but really the critical values. The critical values are the values that make the numerator or the denominator 0. And it's important to understand that it's okay to have 0 in a numerator of a fraction, but not on the bottom. You can't divide by 0. So keep that in mind as we run through these examples. So our critical values are positive 4 and negative 3. We don't have to do any factoring here. So those will be our critical values that we'll use to cut our number line. So let's see, negative 3 is first, and then positive 4. And we already know that multiplicities are going to be useful here. Well, these factors aren't in parentheses. That can throw you off sometimes, but it's really just because they're raised to the first power. So these both have a multiplicity of 1, which is odd, okay? Now, the next thing is when we look at the y values. In a polynomial, when we look at the y values, it's always 0, because the critical values are literally the zeros of the polynomial function. Here, with a rational function, zeros of the denominator are not zeros of the function. They actually make the function undefined. So when we look at when x is negative 3 and we plug that in, our numerator turns into negative 7, which is just fine, but our denominator turns into 0. And negative 7 divided by 0 is undefined. So I'm going to indicate that with just a U for undefined. So whenever x is negative 3, y is undefined. We don't get a value, okay? Now when x is 4, we get 0, or sorry, when x is 4, we get 0 on top over 7 on bottom. 0 divided by 7 is 0. So don't get those confused. Zeros from the numerator output 0. Zeros from the denominator output undefined, or they don't really output anything, okay? Now from here, we need to figure out the signs of the intervals between those critical values. And to do that, we're going to start with end behavior. So we need our leading term. And for a rational function, to get your leading term to decide your end behavior, you have to look at the leading term on top, which is x, divided by the leading term on bottom, which is also x. And then because it's a fraction, you have to reduce it. You have to simplify it. X divided by x is just 1. So the end behavior of this is a horizontal, behaves like a horizontal line at the y value of 1. So it doesn't grow or shrink, it's getting closer and closer to this y value of 1, which means that since both ends of the graph are above the x-axis, the y values on both ends are positive, okay? And then using the multiplicities, we can fill in this middle sign. Since we have an odd multiplicity, the sign that goes here has to be the opposite of the sign on the other side. So since this sign is plus, this sign has to be minus. And again, to check, this multiplicity is odd, meaning that this sign and this sign should be different, and they are. So that's it. That is our total number line chart for this rational function. Very simple if you've already done the work of understanding polynomials. So we're going to do several more just really quickly. Again, I'll try to build in different end behaviors because that's where most students struggle here. You got to get the end behaviors right. So let's see, let's look at our next example, which will be f of x equals, and on top we'll have, well, x minus 4 squared, and on bottom we'll have x plus 3, okay? So here, we have the same two critical values, -3 and 4. -3 has a multiplicity of 1, which is odd, and 4 has a multiplicity of 2, which is even, okay? So those are our x values, and we know that if x is -3, the denominator is 0, so y is undefined. And when x is 4, the numerator is 0, so y is 0. Now we need the end behavior to get us started with our signs. So we need the leading term. The top is factored, so we have to think about, okay, if we multiply it out, what's the leading term? And that's going to be x squared for our numerator. And on the bottom, we just have x to the first. And then you have to reduce the fraction. So x squared divided by x is just x, and that's x to the first. Well, that's x to an odd power, so the right side grows and the left side grows in the negative direction. So that means on the left end of my number line chart, my y values are negative, and on the right side of my number line chart, the right end, my y values are positive. Using the multiplicities, since this multiplicity is odd, I know the sign that goes here has to be the opposite of the sign on the other side. Since this is minus, this has to be plus. And then the even multiplicity tells me that those two signs have to be the same, and they are. So we did a good job here, and that's all there is to it. Throw in this extra multiplicity into play. All right, let's do another. Let's say we have y equals 2x minus 6 over x plus 1 cubed. And so in this case, the denominator's factored. We could factor the numerator. We could pull a 2 out. Makes it easier to identify zeros or critical values. So now the critical values are -1 and +3. -1 has an odd multiplicity, and +3 has an odd multiplicity. We know that if x is -1, we're dividing by 0, so y is undefined. And if x is +3, the numerator is 0, so y is 0. And then the end behavior is going to give us some signs to get started. So let's look at the leading term. On top, the leading term is 2x. The bottom is factored, so if I were to multiply it all out, my leading term would be x cubed. And if I simplify that, this x cancels with one of those x's, leaving 2 over x squared. So what we get is, it's not a negative, so it's not flipped over, but we're dividing by x to an even power. When we're dividing, the ends shrink. They get closer and closer to the x-axis, and when it's x to an even power, they both get closer to the x-axis from the positive side, from the top, okay? So there are our end behavior. So what this tells us is on both ends of my graph, my y values are above the x-axis. Barely, but they're above, so my y values are positive on both ends. And then using my multiplicity that's odd, I know that the sign in the middle is going to be different than that plus, so it's going to be a minus, and it matches here with this odd multiplicity as well. See how quick this is? But the key is leading term and end behavior. If you don't get that, it's going to throw off everything. One more quick example with more factors, okay, just so we really get the hang of this. So the last one, let's say the function is called g of x, and on top we have x to the 5th times x minus 1 to the 7th, that's a 5, x to the 5th times x minus 1 to the 7th over x plus 3 to the 4th times x minus 6 squared. Okay? So our critical values, we have 4 of them now: 0, 1, -3, and 6. So -3 comes first, and then 0, and then 1, and then 6. -3 has an even multiplicity, 0 has an odd multiplicity of 5. 1 has an odd multiplicity of 7. And 6 has an even multiplicity of 2. And then -3 makes the denominator 0, so the y is undefined. And 6 makes the denominator 0, so y is undefined. And then 0 and 1 both make the numerator 0, so y is 0. Okay? Then we're going to get the ends, and then we'll use multiplicities to fill the signs in the middle. So the leading term of this guy, if we multiply out the top, we'll get x to the 5th times x to the 7th, which is x to the 12th. And if we multiply out the bottom, we'll get x to the 4th times x squared, which is x to the 6th. And when we cancel these 6 x's with 6 of those, we're left with 6 x's on top, or just x to the 6th. So the ends grow. It's an even power, so both ends are positive. Okay? So on my number line chart, my y values are positive on both ends. And now it's real quick to get the rest of the signs using the multiplicities. Even multiplicity, same sign. Odd multiplicity, different sign. Odd multiplicity, different sign. Even multiplicity, same sign. We're good to go. So that's building a number line sign chart for rational functions, understanding that some of the critical values might give you undefined outputs while others will give you 0 outputs, and then using multiplicities and end behaviors to put it all together.